Hello everybody, I hope everyone is fine. Today I'm going to discuss one very important question of GATE 2024 where you can see it is said that we need to calculate the small signal voltage gain. So when we have to derive the small signal voltage gain, first we have to see that whether the circuit is biased in saturation or not. Okay, and then we can only find out that what is the small signal voltage gain. Okay, so this is a circuit that there is circuit M1 and M2. Remember here from this circuit you can understand that M2 is the amplifying MOSFET which is amplifying, but M1 you can see that this M1 is direct connected, so it is used for just biasing purpose. Okay, and there is a capacitor C1. This capacitor act as a short circuit during AC analysis, and the AC signal should not interrupt the DC bias voltage. So this capacitor C1 acts as a blocked element for the DC voltages. Okay, before I make the solution, let's go through these few facts that there is terms called as small signal transconductance GM1 and GM2. See, GM1 and GM2 is valid only if the MOSFETs are biased in saturation. Okay, second thing is that this is given that there is no body effect, although if you see that M2 and M1 there is no body effect possible and there is no channel length modulation. So if you compare the output resistance with the resistance RD, so since there is no channel length modulation, we can say that the output impedance of the MOSFET M2 and the output impedance of the MOSFET M1 is infinite. So for this direct connected, the impedance will be 1 by GM1. And if you compare at the output that there are two resistance in parallel like RD and RO2. So if you think that at the output the impedance is only RD, we will talk about it later on. Okay, and there is no intrinsic device capacitance like CGS, CGD. We are just ignoring that. Okay, and as I said that C1 acts as a short circuit for AC analysis. It means that for the AC voltages the equivalent capacitive impedance is very small with compared to RS. Okay, so RS is much larger than 1 by j omega C1. Okay, so now we need to find out the small signal voltage gain. Now if you see option 1 is fine if the small signal Vin is fully appearing across the gate to source voltage of M2, then option A is correct. But first we need to check that the small signal voltage Vin is fully appearing across M2 or not. So first we need to check that about the AC analysis. Okay, so if we do the AC analysis, then we have to open the I reference, which is the current source, and then if you see at the equivalent circuit, then you can see that there is a voltage division because we are doing the AC analysis. So C1 is shorted, so you can see that there is a voltage division. So the small signal voltage Vin is not appearing across the fully appearing across the gate to source voltage of M2. So option A is not possible. Okay, so we have to look for the other options. Before going to search for the other options, means to find out the exact solution, one thing I should tell you that I have made some other slides which is going to describe about the DC biasing conditions, which I will tell once I do the AC analysis and get the correct solution. So here is the AC analysis. Although I haven't not replaced the MOSFET with the small signal diagram, I have just replaced means the current source by an open circuit. Okay, and replace the capacitor with a short circuit. And here I have also replaced the direct connected M1 with 1 by GM1. I will explain why I have replaced this direct connected with 1 by GM1 in the later slide. Here I have replaced M2, transistor M2 with the small signal diagram. Okay, where the voltage across the gate to source is VGS2. Okay, and that voltage is going to modulate a current from drain to source, which is given by GM2 into VGS2. Okay, and since there is no body effect and nothing, so the voltage should appear across the parallel combination of RO2 and RD. And let me simplify it much more, that since there is no channel length modulation, so RO2 is infinite. So the parallel combination, what you will get only RD resistance. So the entire GM2 into VGS2 current is flowing through RD. So what will be the output voltage? It will be minus GM2 into VGS2 into RD. Earlier that there is a voltage division. So the VGS2 is not equal to VIN. So there is an additional voltage drop from VIN. There is an additional voltage drop at across RS. So what VGS2 is equal to? It is equal to VIN into the series combination of RB and 1 by GM1, and which is divided by the total resistance which is seen by this voltage source. Okay, so this is my VGS2, and I have already said that your V out has to be equal to minus GM2 into VGS2 into RD. So now if you see the voltage gain, you will see that there is a fraction of GM2 into RD. So that fraction is nothing but RB plus 1 by GM1 divided by RB plus 1 by GM1 plus RS. Okay, so this was a very simple question. Okay, so now option B is my correct answer. Okay, and now we should discuss about the DC bias and some other parameters also. So here is a function of the DC bias circuit. So here you can see that there is an IRF current which is flowing, and this current IRF should flow through the Mosfet M1 only if the gate to source voltage of M1 is greater than VT. Then only there is a possibility that there will be a channel in this M1. Okay, also to make this circuit operational, the VGS1 has to be greater than the VT1. Okay, and this diode is always in saturation. That we will discuss that why M1 is always in saturation. Means this is actually diode connected and M1 will be always in saturation. Now you can see that there is a drop across the gate to source of M1, which is VGS1, and there is no current which is flowing through RB because it is not possible to have a current which is flowing through the gate. That is not possible unless and until there is any leakage or anything is happening. That is far away from reality. So the entire voltage VGS1 is appearing across VGS2. Okay, so this I reference will induce a voltage which is VGS1. Say, so that VGS1 is equal to VT1 plus this root of 2 into I reference into mu n into Cox into W by L1. So you can see that there is a VGS is greater than VT1 by this amount, which is controlled by this I reference. Okay, and since this VGS2 is developed, okay, and if this VGS2 is greater than say VT2, which is the threshold voltage of the M2 transistor, and say your drain to source voltage of M2 is greater than VGS2 minus VT2, okay, then it will be in saturation, and then there you can see that there will be a saturation current which is ID2 that will be flowing through here. Okay, so we have to ensure, design RD in such a way so that your VDS2 is greater than VGS2 minus VT2, where your VT2 is the threshold value of your MOSFET M2. Okay, so this is how we bias the circuit in saturation. Now I'm going to discuss that how this M2, this diode connected, always is in saturation. If you look into the transistor M1, you will see that VGS1 and VDS1 is equal. So anyhow your VDS1 should be greater than your VGS1 minus VT1. So that is why it is always in saturation. And now if you replace this diode connected with its small signal diagram, then you will see that the equivalent impedance across it is nothing but 1 by GM1. Okay, as VGS and VTS both are same over here. Okay, so when you are calculating the output impedance is nothing but the drop across the VDS, and which is divided by the current which is flowing, and RO1 is very large. In the question it is given that there is no channel length modulation, so it is infinite. So you can see the resistance across this current source is gate to source voltage, or you say the drain to source voltage divided by the current which is flowing. Okay, so you have seen that GM1 into VGS is equal to the IDS, means the current which is flowing from drain to source. Okay, and we are not considering the RO1, it is impractical, it is infinite. Okay, so the equivalent impedance from drain to source is equal to 1 by GM1. I hope now it is clear. So whenever you have a diode connected, first point is that it has to be always in saturation, and the second point is that it is the equivalent impedance across this diode connected. Diode connected means drain and gate are connected to each other, and it will ensure that it is in saturation, and then you will find out that the equivalent impedance across it is 1 by GM1. And when you are computing it or evaluating it from the drain end, okay, remember this one. Hope that all the doubts has been cleared in this question, and still if you have any doubt then please comment. Okay, and if you don't comment then we will not be able to understand that where we are going wrong or where you are not able to understand. Okay, so if you have any doubt also, before commenting, just a suggestion, you can again recheck the video, just rewind it and again recheck it. Okay, so you should apply your brain and you should think that why I have said this or why I have said this. Okay, so this will actually help you to have more intuition. Okay, thank you everyone, bye.